there was some issue. So we have G1, right? And this is G in GA, such that the determinant is a unit. Okay. And we have because of the Iwasawa decomposition, we have a decomposition for G1, which is n A times, there are two groups here, A sub 1 and A superscript 1, and times K. Okay. And just to clarify, this is all things. So A1, my Siegel set will be defined in terms of this data, right? So I'll have an element here, an element here, which would actually be in something called AT, right? I also have some. So this are called omega n, this are called omega a. So these are supposed to lie in compact sets, and this are called K. Okay. And the point is, A1 is going to be, A1 consists of elements. A1 is a okay. So first of all, A1 is supposed to be all elements of determinant 1 inside A greater than 0. So A1 equals G in A greater than 0, right? Such that determinant G equals 1. Okay. And A superscript 1 is G in A such that the individual entries, so okay, let's call it A, such that the individual entries, right? So AII, which are the diagonal entries, they should have absolute value. I mean, they should have normal. Okay. So none of these are central. The center has been taken out when quotienting G1. I mean, the central part that we want has been taken out when quotienting GA by Z greater than 0. That is G1. Okay, so essentially, this is what's happening. Okay.
What does mod AI equals 1 mean for rational numbers?
Huh?
What does it mean for rational?
Adelic norm.
Adelic norm, but suppose we are dealing with a real place.
Yeah, then the usual real place, meaning this is the product of absolute values at all the places, both real and complex.
No, but I'm thinking that the Adel group, let's look at the component wise, and I'm looking at the component.
So absolute, so something here looks like
absolute value
T11, T1, so just over Q, T11, T1, T22, etc. Absolute values
of individual entry, but they are real numbers, so the absolute value is 1 is 1.
No, it's the adelic norm that is 1, no?
Norm it is.
Norm adelic norm that is 1, so product will be 1, no? Product of all those things, not individual.
Okay.
Norm it is.
Yeah. That's here. Over here you will have only Archimedean entries. Okay, here the typical thing, so if I had F equals Q, I'm just going to have something Tii, T11, T1, T22 and so on. Tnn. Okay? And then at the Archimedean place, and then 1, 1, 1, 1, 1 everywhere else. Okay? So this is at the infinity place. Infinity F equals Q. Of course, if there are many components, I'll get the same T11, T11, T11 at each of the infinity components, and then 1, 1, 1, 1, 1. Alright? So that's.
It's like an SLN component of.
SLN component, why?
Determinant.
No, so it's basically, look, it's like when you take the ideals and you separate them out into an R plus and a norm 1 ideals.
It's a subscript. So over there, the condition that I put is that it's, we are looking at Archimedean basis. And along with that.
And determinant 1.
Yeah.
And it's a diagonal. And not just that, no, it's A greater than 0, so it's the same entry at all the Archimedean places. Yeah, it's not a big deal. You want to somehow take out the determinant, the part where the determinant grows. As I said, if you're looking at SL2R, then this corresponds to the subgroup Y. Y to the minus, Y to the half, Y to the minus half, Y to the half, Y to the minus half. Okay, and the ratio, or if you have A1 and A2 in general, the ratio A1 by A2 and absolute value being bigger than or equal to T corresponds to that part in the fundamental, in the upper half plane, which is larger, which has imaginary part greater than T. Okay, so that's the model. Okay, so, and we had the Ziegler set, right? So the Ziegler set was other form, basically it looked like, sorry, and I'm now not, okay, so G was equal to the form omega n A omega A and K, and the point is this A was in some AT, some T greater than 0, right? AT was defined by AT was simply A in A1 such that alpha I A was greater than or equal to T for 1 less than I less than or equal to n minus 1. Okay, so this is my set. So Ziegler set looks like this. These are all in some compact set. So the omega n's are in some omega n compact in NA, and the omega A is in omega A compact in A superscript 1, and K is of course anyway compact. Okay, so this is my Ziegler set, and we have already said, look, there is a Ziegler set, so that and the main point was that there exists a Ziegler set. So okay, might as well restate the theorem and then keep going. There is a Ziegler set. S such that so first of all, GA is nothing but G1 is nothing but GF times that times this Ziegler set. So basically translates as the Ziegler set exhaustively. And the second one is that if you translate the Ziegler set by GF elements, the intersection, the number of translates that intersect S is finite. So I think I call it X maybe sigma, and that is gamma in GF. The definition gamma in GF such that gamma S intersection S is not empty. So then what we know is that we can have this to be finite. Okay, so this is the normally use that one first. But okay. And the property holds for any bigger Ziegler set though. Yeah, I suppose I will use it since I read T code around here. Okay. So anyway. I don't know that if T goes to infinity, actually the Ziegler set, if T goes to infinity, the Ziegler sets are getting smaller at least. So, larger. Sorry. Going towards the first plane. Sorry. Right. So anyway, so let me just okay. So what? Yeah. So the first thing to say is that look, in order to estimate. In order to show moderate growth on GA, it's enough to look at the Ziegler set. Okay, so for that one I have to do a number of lemmas. Not very difficult, but it has to be done. Okay, so series of lemmas, I guess. Which essentially say the following. So if G is a Ziegler set, yeah, right? So obviously, we have inf gamma g less than or equal to, the norm of gamma g is obviously going to be less than that of g. That's trivial, but the point is the inequality works in the reverse direction. So with a constant, of course, but we show, let's see, norm g is not equal to constant times norm g for something. Okay. So t is of course fixed, right? So first of all, yeah. So first of all, I should make this comment that if G lies in this set, so note, okay, before this proof, if G lies in this set A omega n, omega n A omega A times n, then I can of course take the A this side, and so that's equal to A omega n A inverse A omega A n, and the point is, yeah, I want this to come to the other side. So what did I do wrong? Sorry. A inverse omega n A, yeah. So this is of course again a compact set. Okay, it is in 80. So then I can always write this therefore, so I can think of G as lying as A times omega G for some compact G, omega G compact. Alright, so with that in mind, right, so I need to show that, so then essentially it boils down to just looking at A, right, so I need simply norm A is less than or equal to C times norm gamma A for all gamma G. Right, and A in 80. Okay. So this is easy. So yeah. So what is? So I have A greater than 0. So what does its? So what does a general diagonal term look like? It looks like AJ is say TJ, TJ. TJ 1, 1, 1, 1, and so on, right? Okay. And the norm of A is of course nothing but sup over J. So maybe I just assume, okay. So assume F equals Q, makes sense. Okay, otherwise there will be some power of T coming in all the time. So assume F equals Q. So then in fact there will just be one TJ. Right? Okay. So then what happens? So and of course, what is the norm of A here? Well, by definition, it's the supremum of J, Tj, and Tj inverse. That's the norm, right? By definition, just sup of all the individual entries and their inverses. Okay. So what one realizes then, right? So if gamma is in GF, yeah, then of course there is some ij for which gamma ij is not 0. Such that gamma ij is not equal to 0. One of the entries is non-zero, of course. And then of course what we see is that Tj times mod gamma ij is obviously nothing but gamma ij into ajj, right? Remember the matrix A is just going to multiply each column, I guess, by column by ajj, right? And so this is nothing. This is of course definitely less than or equal to norm gamma A at infinity, or gamma A at infinity, right? Okay, which is of course just the norm, which is the norm. So okay, and similarly. You can do the same thing for the inverse, right? Tj inverse times whatever mod gamma ij, right, is similarly going to be, so what this tells, is similarly going to be less than times whatever gamma ij is going to be less than or equal to gamma a, right? But of course, what is the norm of A? It's exactly sup of these things, right? So the net result is going to be that I get Tj, so net result is I'm going to get that norm A is less than or equal to gamma for any A, and therefore then for the index. Okay, so that's simple enough. So what this tells you is that I can indeed just translate everything and at most get a constant. So of course the constant will come from the rest of the stuff, but okay. The second thing which I'm not going to prove, as I said, there will just be a series of lemmas. None of them are particularly hard, but they need to be stated, right? So the second lemma is the following: that instead of looking at norm A to the m, remember finally I want to show that something is less than norm G to the m, right, or height to the m. So instead of doing that, I can look at the following thing, and so let's look at beta A, which is the product of the absolute values of the simple roots. By the way, I should say that although this is a proof technically only for GLN, right, the way it's formulated, it will work in general. So for example, here I have the product of the simple roots and absolute value coming in. One can just take the analogous thing. Okay? So suppose you have this, then there exists C1, C2, M1, M2 such that C1, this is for any A in A, C1 beta A to the M1 is less than or equal to the norm of A is less than or equal to C2 beta A to the M2. Okay? So what we are saying is, as far as moderate growth is concerned, whether I bound by beta, some power of beta A, or I bound by some power of A amounts to this, norm A amounts to the same thing. So if I want to prove moderate growth, it's enough to bound by some power of beta A, because these two are comparable. Alright? So this is true for anything. So in particular, on a Ziegler set, right? So on a Ziegler set, I have basically again beta A M1 less than so up to some constants omega n omega A omega A times k. This is less than beta A to the m2. So on a Ziegler set, this is what happens. And finally, this is the one we would like. So we would like to know what happens when you translate a compact set and so on, how that behaves with respect to the norm, and that's answered by the next lemma. Okay, so lemma. Let's see. Right. So let lemma 3. Let C be a subset of G1, which is compact.
So that element beta A, that number would just amount to the mod A1.
Actually, it's just mod A11 by mod
ANN.
But as I said, one would like to state it like this. Yeah, so of course he's right. Right, so each of these things are just quotients of mod A11 by mod A22 times mod A22 by mod A33, etc. And all of those will cancel and you will be left with mod A11 by mod ANN. And I could have written that, but this tells you where it came from and that it's actually the product of the simple roots. Yeah, so it will then allow you to, in principle, generalize for other things. One could have, of course, just written that down. It's a simple exercise. Remember that you're inside A1, A superscript 1, so I'm sorry, A subscript 1, so the determinant is 1.
So that said, this should correspond to one of the longest elements of the file.
No, where is the while group here? No, I mean, okay, yeah, sure. Anyway, so, okay, yeah, So one is equal. Yeah. So suppose I have a compact set. Then here's what I want to say. Right. There exists C greater than 0. Okay, and m greater than 0. Right. Such that what for all x, right, in GA, G1, I guess, the number NC in capital C is equal to the cardinality of GF intersected by x C x inverse, right? So you translate you conjugate a compact set, that should be less than some constant, so we call this C1 because it's already C1 times norm x d. So translation of a conjugation of a compact set by some element x, basically if you have such a thing, then the number of elements in GF intersect that compact set behaves again like the norm of x to the n. Okay, so again, everywhere the point is you can move sets around in various ways, either by GF or by conjugation, etc. And the worst that will happen is you'll pick up a power of norm g to the n. That's the underlying point of these lemmas. Right? So eventually you want to estimate something on G1, but what we'll do is we'll take a Ziegler set and then we may have to move that Ziegler set around a bit or whatever. That's okay, because whenever you move things around, either in this way or by a GF, moving by GF lands you in the Ziegler set, conjugating like this, okay, allows that. I'll just, before this, I'll prove this lemma, but I'll just point out a consequence, namely that if you have x, instead of this, you can take x, so consequence, as I said, none of these are hard, right? If you take GF intersection XCY, right, that also looks like, so let's take N, I don't know, maybe I should call this NX rather than call this NX. If I take NXY, which will be defined as a cardinality of GF intersection XCY, XCY, that will also be less than or equal to constant, some other constant maybe, no, x to the n. Okay, why is that? Well, you see, if I have gamma, say delta in the set, right? In the set GF intersect XCY, and I take let's say gamma inverse and also gamma, so gamma like this, then I guess what, gamma inverse delta or delta gamma inverse, what is that, where does that lie? That lies in y, okay, maybe the wrong, x c y times y inverse c inverse x inverse. So these two things cancel, so I'm just left with x C inverse x inverse. So I can apply the same lemma. I can apply the lemma to this situation, and the same thing is true. So instead of conjugation, I can also just translate arbitrarily by x on the left and y on the right, by any two elements, and I'm still going to pick up only a factor of norm to the, and it's going to be for the same x. Okay, so if I have x on the left, then what I do on the right doesn't matter from the point of view of the norm. Okay. Right, so armed with these, okay, maybe I can spend 2 minutes on proving some stuff and then. Okay, so let's just prove this lemma 3. What shall we do? Yeah. So suppose I do the following, right? So notice that NX, what I call it, right? So NX is invariant by translation by under left GF translation, right? So I can just move cardinality of the set obviously doesn't change if I move to the left. So I can just assume, X is in a legal set, right? Okay.
In that statement over this,
Which one?
nxy is less than equal to the last one, C2, norm x power, I can't see.
Norm x power m. M, same.
Same.
No, it's this one, right? So it's the same x that comes. So whatever x, I'm just applying to the C prime rather than C, and therefore I'm getting C2. That's all. Okay, so it's the same. And it doesn't matter even if you are a different one. So we just want some power, we can be pretty careless about it. No, I guess it does matter because we don't want the exponent to vary with y, but yeah, okay. Alright, so here I can assume what? So I can assume that x is in a Ziegler set. Ziegler set. Okay, so then once you do that, right? So, yeah. So in that case, of course, x is in G infinity times C for some compact set. Right? And you can actually really by conjugating by a suitable C by a suitable set can assume in fact that x is in C infinity. Can in fact assume x is in C infinity, x is in G infinity. Okay. Alright? And now if I have gamma in this set GF okay. So if I have gamma in GF intersect x C x inverse, right? What can I say? Well, I know that norm of gamma is definitely less than or equal to constant times. Well, it's in here for sure, so it's just less than constant times norm x inverse, but norm x inverse is norm x, so that's just norm x squared, right? Okay. Alright. So now if I have V, say compact neighborhood of one in G1 such that GF intersect BB inverse equals 1, right? So just take a small enough neighborhood so that BB inverse intersects GF. One GF remembers it discretely in there, so there's no problem, right? Take a V in V, a gamma in GF. So and gamma in this set, GF. Okay, I should have given it a name, but anyway now it doesn't matter. CXC inverse, right? Then what we know is that norm of gamma V is of course less than or equal to some C1 times gamma, norm gamma, right? Because this was a compact neighborhood. Yeah, compact neighborhood, so that's okay. And that's also, I'm saying, less than some C2 times norm x squared, right? But gamma V, where is it? It's in x C V inverse V, right? Let's see, gamma. Gamma V is in x. Yeah, I can put it here. V, that's okay. Sorry, x inverse V. Alright? And which is of course again in some G infinity and omega. This is of course in GF. Alright? So what this means is that gamma V is actually in the set G, G C squared. I'll explain this notation, norm x squared omega. This is what I'll call T. Okay? And what is GT? You see, GT omega is going to be G in G infinity omega such that norm G is less than or equal to T. Okay? Yeah. So you look at this set, but now you see the point is you have gamma V inside this set, okay? And this is a set of finite measure. GT as set of finite is a set of finite measure. You can change that. So GT as finite measure. This is the point. Okay. Alright, so now that you know that, we are essentially done. Good, let's have half an hour. See, if you know that, you see, you have the disjoint union of gamma V, gamma in this set, this was the set Sx each time. So gamma in Sx, gamma V equal is contained in G C2 norm x square omega, right? So volume of this whole thing is obviously volume of this whole thing is of gamma V is obviously contained in this volume, right? Volume of G C square norm x square omega, but that is contained, but you know, where is that? So where is our estimate for gamma? Yeah. So we already have this thing being less than C something times x square. Okay? Right? So gamma V is in that. So the whole thing is going to be less than or equal to constant times some x norm x to the t. Okay? And the point is this is nothing but volume of V, right? Or less than times nx. So you get an estimate for nx. Nx is estimated in terms of the norm. Okay? So let's keep this. I know I went a little fast through this, but I just the basic point I need to take away is that I have something like this. Conjugating only produces an extra norm x to the m, and so you can move sets to the left by x, and it doesn't matter what y you translate by on the right, you're always going to get. Okay, so that's the key point. Okay, so now we come to the very last part of the proof, where I will, I think, only barely pretend to give a proof, but let's see. It's actually not so hard, but and also relatively elementary, I have to say. Okay. So what's the? Okay, but unfortunately, it's going to involve a lot of formulas. So I think I'll probably just stick to it. So here's what we want to prove. Okay. So remember, we want to prove something is of moderate growth, right? So we have a Gus form, and we have assumed it's in L2 and so on. And sorry, we have a Gus form, and we want to prove that it's in L2. So we will actually prove that it's bounded, but we'll do more. So what we really need to prove is phi of A omega, right, is less than or equal to constant. We'll actually prove this. Okay, minus m over m greater or equal to. So we'll actually prove something much more than bounded. We will see that it's less than beta 8 to the minus m for m greater or equal to m. So, okay, so we will prove something much stronger. This is when what? When A is in AT and omega is a compact set. Omega lies in a compact set. This is the form, right? Because to prove moderate growth, it's enough to prove it on a Ziegel set, and any Ziegel set looks like this. Looks like something in AT times a compact set. So this is what we need to do. Okay. Yeah. So first, let's take F such that, okay, phi convolution F equals F. Phi. We can always do this. I'm going to do something. Okay, so phi convolution F is, of course, my formula is integral phi of H G F of H inverse GH F of H inverse DH normally, but I can just assume that that this is true. So instead of saying phi, I can assume that this. So this is true. So there exists f. So take maybe f1. So take f, which is of course just f1 of H inverse. So take f such that this is equal to phi. Okay. So I don't want to carry the inverse everywhere because, well, when I was doing it, my source, which by the way is an article of Goldfeld and Jacquet, doesn't have the H inverse, so I don't want to make things incompatible. Anyway, it doesn't matter, right? If I had an H inverse here, I would just change the function f of H inverse to be the new function. Okay, so now what I have to do is to, so I have such a thing, and now I will use the fact that it's a convolution to get something out of it. So let's see. So first I will use the Iwasawa decomposition. So I will write my phi of a omega as, okay, so first of all, phi of a omega will be written as integral, well, many integrals, Iwasawa decomposition phi of u b k. Oh, so, okay, so I'm going to rewrite this, by the way. Instead of writing it like this, I'm going to write it as phi of h f of, so h goes to g inverse, so g inverse h. Okay, change variable. So when I do that, I will write my h as u times b times k. Okay, so here h equals u times b times k. This is Iwasawa. So this is in A. This is in A. In fact, A1, so on, or yeah, just A, and this is in K. Okay. So I have phi of u b k. Then I write f of w inverse A inverse u b k. There will be a du, there will be a delta b inverse, this is the modular character, db dk. So I just decompose using the Iwasawa decomposition. This is what I get, right? So this is my g inverse, here is my g, here is my g inverse, here is h again, and there is h. So nothing really has happened here. Alright. Yeah. So of course this is on G1. So really this is in AA intersect G1. This term. This B lies not in technically in AA but in AA, well, lies in that but intersect G1. Okay. Everything is of course intersected with G1. F has compact support, of course. The F that we take, F has compact support. So keep that in mind. So now, what do we do with this? So here is a point. Again, I can conjugate and move things around a bit, and I will at most use some norm factor, right? So remember that A inverse UBK, right, is of course nothing but A inverse A inverse BK. So again, of course, if H is in the support of F, right? A inverse B is in a compact set. So A inverse B lies in a compact set. Okay. All right. So basic idea. You have some big integral. You first write phi as a convolution and use Iwasawa decomposition, and this thing here, I have A inverse UBK showing up over there, but that can be written as A inverse UA, which once again lies in a compact set, and A inverse B, which lies in a compact set, and K. Okay, so this part, of course, this automatically lies in a compact set. Okay. All right. So if I do this now, we'll do the following. Yeah, so this is the kind of trick. And okay, so let's before the trick. So remember that phi is so now phi is left invariant under NF. Of course. In fact, under much more than NF, but certainly under NF. Okay, so what does that mean? So I can, my integral becomes, so this, so have, means get the following integral. So nf by na, or na by nf. And now I will write this as a sum. Okay, so I write sum gamma in nf. Right, so I basically again split the measure on A as something coming from Na by Nf and a sum over Nf. Okay, so not an uncommon trick in this game. F of, so there I have omega A inverse U, but here I'm putting a gamma. So basically wherever I have UBK, that is H, I'm replacing it by a gamma H. Okay, so I replace it by a gamma H. So I have gamma UBK, so that's the sum, okay, and then I have what's left, phi of UBK, and then I have du delta B inverse dB dk. So idea is just to, okay, so now is the, okay, now is the trick if you like. In the little reminiscent of Sandeep's lecture, we are going to introduce an alternating sum. Okay, so here is the thing. So here's what we're going to do, right? So delta is going to be the simple roots, set of simple roots. Alpha I, of course, 1 less than I less than 1. Now what we'll do is we'll take a theta, okay, to be a subset of delta. Okay, and now we let V theta be the subgroup generated by n alpha, right, the root space corresponding to alpha. But which alpha? For those alpha for which there exists a simple root alpha I such that alpha minus alpha I is positive, right? So you, okay, it's positive, equal to sum of positives. So I mean, which the point is we're going to get a parabolic, right? So the V theta is of course going to be the uniform radical of some parabolic. Of some parabolic P theta, say P theta, and I'll write that. So if we write P theta as M theta N theta, Levy decomposition, right? Then I'm going to set N theta to be M theta intersection N, right? And N in that case will be N theta times V theta, and the point is this is normal. Okay, so I'll just, maybe I'll work out some example just to tell you what's going on. Okay, the idea is we have got some parabolic and we've got some unipotent groups, and I'll just show you, for example, for GL3 what they are. Okay, so it becomes clear. It's all very concrete, right? So for GL3 there are just two roots, alpha 1 and alpha 2. So what are the possibilities? So first of all, we can take what are the possibilities for theta, right? So let's take n equals 3. Or before n equals 3, we can point out. Yeah. So example, e.g. So I can of course take theta to be the empty set, right? And in that case, obviously, there is nothing in V phi. Right? So this is going to be 1, and then P will be equal to G, because unipotent radical is just 1, so P will be equal to G. right? In that case, P is P phi will be equal to G. And then in that case, M phi will be G and G intersection N. So M phi is G and G intersection N, so that's N phi is going to be N. Nothing new. The other case that one would take obviously is when theta equals all of delta, in which case you get the minimal parabolic, right? So if you take the standard choice, then you just get Borel, right? Minimal parabolic, right? And in that case, M delta will be the torus, usual diagonal subgroup, right? And V delta will be N delta will be 1. So N delta will be 1, and therefore, of course, V delta will be okay, right? But let's take n equals 3. So this is always true, this stuff. But if I take n equals 3, what are the possibilities, right? So delta equals alpha 1 and alpha 2. Right? So there are just two roots, and the only subsets. So the positive roots are going to be alpha 1, alpha 2, and alpha 1 plus alpha 2. Right? That's all I'm going to have by way of positive roots. And so what are the possibilities, right? So if I take theta say to be alpha 1, right? Then what is V theta going to be? V theta will be generated by n alpha 1 and n alpha 1 plus alpha 2, right? So that's just going to be 1, 1, 1, star, star. Wait, sorry. No, that's right. This is alpha 1 x star star. Okay. Just to get an idea, right? And in that case, V theta will be this. Am I right? Yeah, it's okay. And therefore, n will be the remaining thing, right? So n alpha 1 will be, so m alpha 1 will of course be the Levy 1, 0, GL2, 0, and then of course n alpha 1 will be nothing but the other part. What's missing here? 1, 1, 1 stuff. Okay. So that's what it looks like. You can easily work it out for the other one, alpha 2. Okay, so this is what we have in mind. Yeah, you just get different unipotents in the two different cases. So in the other case, obviously, I will get star and star here, and this n alpha 2 will have a star there and a 0. The reason we're doing this is the following. Okay, so we're going to introduce the following object. 7 minutes. Let's see how this goes. So here is the trick, if you like. But as I said, we introduce a certain alternating sum -1 to the mod theta, right? The integral over v theta, the adelic points of v theta a, right? Times summation gamma n theta f of that object, f of omega inverse a inverse gamma v u v k, so dv. Okay, so we are integrating basically on v theta a, this object. That's the, and this sum I will call on theta not equal to 0, of course. We don't want the empty set. Okay. Yeah. Alright, and I'll call this whole thing point, alternating sum, so I'll just call it point. Okay. So now, here is the point. You see, I can decompose my n as v theta times n theta, right? So I have some integral where was my integral last? It was somewhere here. I have an NA by NS. I will decompose that as an integral over each of these individual things, and because v theta is normal in n, I can switch the order of the integration. So I can do the v theta on the outside and the n theta on the inside. Okay, so I don't want to write out the whole formula again, but roughly speaking, what will be involved is I have these integrals, but I will have NA over NF, right? Times all this stuff, right? This sum over v theta of A. This is what I'm looking at. Some stuff phi of UBK du. Okay, and then of course there's dB, dk, and so on. Okay, all right. So this can be decomposed further. This integral can be written as integral over v theta A. So I should have adopted Sandeep's notation of putting a box, but okay. Vf by n theta A by nf. Okay, and then there's the same stuff. Phi of UBK d. That's the next step. And now, okay, I have that. All right. Yeah, I guess the point is, you see, since I've integrated over VA, right, that I anyway have, if let's do it like this. The point is, okay, I have this object times phi u bk, okay, and then I have dn theta du dn theta dv theta, okay. So here is the point. Because of the cuspidality condition, I know that the integral over, so I have broken up my integral, so this ubk also has to be broken up. It's no longer u. This u is actually equal to nv or uv. Let's see. V theta, let's put the variable, and n theta. Right, so this du also will become dv theta dn theta. Okay? And you have a cuspidality condition which for phi, which will ensure that all of these things are zero, yeah, except when so I introduced an alternating sum, right? So when theta is phi, then there will be there's nothing to do, and that term will remain, but all the other terms will go away. That's the point. So whatever I started with is actually equal to this whole thing times some alternating sum. Why have I written it in this way? So this is the key point, right? Because now I can actually use, so there is this thing in here, right? And I can kind of estimate this thing by using the Poisson summation formula. Okay, so that's the point. So I'll maybe say I'm going to take till 35. We started 3 or 4 minutes late. So I'll see what I can. Okay. So you see, we have this n is equal to v, v theta. So that if I look at the Lie algebra, and I have n theta, right? Like so. And then I have transpose n likewise, which will have the opposite thing. Okay, transpose v theta. So the point is, by the way, you can do this on any group, but if you took an arbitrary group, you need to use the exponential map. Because we are in GLN and I have a unipotent thing, I can just think of it as 1 plus x, where x is unipotent. Okay, so that's the only real saving in this sense. So we have a pairing between n and transpose n. Right? There's a pairing between n and transpose n. Right? To see what is the pairing, well, we'll simply take x, y to trace of x, y. Okay, that gives me a pairing. And using this thing and using that character, I can therefore get a summation formula. So you have this alternative, this alt, right, which is equal to summation minus 1 to the theta here, and that's v theta a, right? Some let's say psi in n theta f right? And this big expression, omega inverse A inverse, and now I'll have something like 1 plus psi times 1 plus x, okay, u, v, k, etc., okay, and a bunch of integrations, okay. The point is, you can now use your own n theta f, and you can use Poisson summation formula on n theta f, because theta is in a abelian situation, right, where the Lie algebra, and we can change variables and get ourselves to the Lie algebra situation, right? And so finally, we can change variables, use Poisson summation, and having done that, we will be reduced to the following situation. Okay, so sorry, here I'm just obviously being very, very sketchy. I don't have time. Half an hour would have done it, but okay. So basically, change variables. So remember, Poisson summation formula roughly says, so if you're on R and Z, it says summation f of n is equal to summation f hat n. So likewise here you have a lattice, nf inside Na, and you're going to be using Poisson summation for that. You have a dual thing which is transpose n. So you get the Fourier transform on transpose n, and that's what happens. Okay, so it's quite straightforward. So change variables, use Poisson summation formula, and that will bring you to the following situation. We'll end up with some delta of AB inverse, which is the modular character. There will be some sum lambda in transpose NF, okay, and some integrals, okay, over NA of some of this thing, of this form, of FW inverse 1 plus x times A inverse, U A inverse, BK, etc. There will be a character side place x A inverse lambda x A inverse lambda A. Okay, so this is a crucial point. Now, the point is, all of these things, x going to this stuff will basically lie in a compact set. So the x going to all of this thing, delta AB inverse times f of whatever, right, is a compact. So you take this family as these things vary, that's a compact set in the space of Schwarz-Brouwer functions. Schwarz/Schwarz-Brouwer functions. So Schwarz-Brouwer functions are of course locally constant functions at the with compact support at the p-adic places, and otherwise Schwarz functions are there in place. Last lemma, which I will not prove but actually is relatively elementary. Says the following, right? And this will more or less complete the proof. Suppose B is a compact set in the space of Schwarz-Brouwer functions. Right? And on transpose of Na, so adelic points of this V algebra, and let M be greater than 1. There exists C greater than 0 such that for all B in B, all phi in B, and A in AT. So I get a certain sum lambda in T and F. That's what will be involved. Phi of A inverse lambda A in absolute value is less than or equal to C times beta A to the minus n. And where is this? This sum, of course, lambda is taken over a certain set. Let's do the following. Okay, so I'm going to take those lambda, essentially, so Find something more. Okay, yeah, so let's do it like this. So sum is taken to lambda, the sum is taken over lambda not belonging to some transpose n theta. So if there is for some theta not equal to 5. So suppose it belongs to theta, if it belongs to one of these things, it doesn't occur in the sum, you take only the others and you can estimate this, right? So, okay, explicitly lambda has the form summation lambda alpha x minus, it's an element of the Lie algebra after all, so it's an element in that space. So then I will just take summation alpha lambda minus alpha not equal to 0, sum over those alpha such that this is greater than summation alpha I 1 less than I less than minus 1. So anyway, I'll quit here. I apologize, I know it was pretty sketchy at the end and fast, but yeah, so let me stop there.
Alright, let's thank Ravi.